All right, here we go. Chapter 3 and Chapter 4, motion in 2D, um, and forces are huge. I'll just tell you that right now. Motion in 2D will probably be the majority of your work. 3D, not so much, but we'll get to that idea. So we'll go through vectors, centripetal motion, multiple dimensions, and projectile motion. Projectile motion is one of the section that people find the most difficult, but I think the key comes back to vectors and understanding pretty much everything can be broken down in an XY plane, and that should help a lot of people kind of focus in on their efforts. So here we go. Maybe. There it goes. So, sorry. One dimension, x-axis, you went from point A to point B. Two dimensions, okay, it's x and y. You've gone up and to the left or right, whatever. Three-dimensional, you went up, forward, and to the left. I mean, if you think about it, that's three dimensions, x, z, and then y. So it's really kind of hard to put into a perspective on a problem because typically you'll break every three-dimensional problem down to two dimensions. So examples, scalar quantities. Basically, scalar quantities are just numbers. Everything down below, numbers. Hat size. Yeah, a number. Interesting. Anyway, moving on. So, example of vector quantities. Force, force with a direction, linear displacement. So, again, linear displacement, you have 35 miles to the north, 35 miles to the west. It is a vector quantity. A scalar is just 35 miles. Doesn't give you any direction. 35 miles. That could be over there, could be over there, over there, over there, over there, back there, over there. Maybe up there, down there, over there. You get the point. So, linear velocity, again, you have to have a direction. So, without the direction, it's just a speed. Linear acceleration, again, without the direction, and the directions can be simple, northeast, southwest, and then some variation of that. Then we'll start getting into, we'll probably start using, and the bad news, I'll tell you right now, if you're in just physics, you would use just degrees. In AP, they want you to be able to use degrees and radians. We'll talk about radians once we hit there, but you should understand. So here we go. So scalar math, it's just your normal addition direction. Got it. So a vector, here's your distance, basically length is your magnitude. You'll hear that term. What is the magnitude of the displacement? What is the magnitude? What is the magnitude? It is the number. So basically the size of the vector quantity. Then the direction. Pretty much every time you have one of these, you have two components. You have the magnitude and direction. They just say, what is the vector quantities? That's what they're looking for. It's the size and the direction. So typically the direction is degrees. And the hard part is, example for this one, the way I would assume they would label it, I would say like 27, 30 degrees north from east. So we'll talk about labeling those a little bit easier later. So vectors. So if you go 2 meters per second east, see how the arrow got a little bit bigger? 4 meters to the west, -4. This is one of the hard problems they can say. Notice how 4 meters to the west, -4 meters to the east. So depending on how they're quantifying that, in fact, I would argue, depending on the velocity you're showing there, to the east on that one is not the best. So little x, 1 meter to the west. So the idea is your arrow should be indicative of the magnitude and the direction. We'll talk about that. So here's a simple one. You have velocity at an angle, 30 degrees, velocity east, velocity north. So if you remember your trig right off the bat or have read, you should be able to go, ready? Sine and cosine. You will use sine and cosine a ton. I typically will stay with sine and cosine. I do not use tangent very much. So, example. So using the sine cosine, you are trying to find, in this case, you're trying to find B. So you sit there and say A, B, C. You could sit there and say the velocity east. So in this case, 5 times the cosine of 30 gives you the velocity east, which is 4.66 meters per second. We look back, does that make sense? Are we going more east than we're going north? True. And then the same thing, the 5 times the sine of 30, that gives us 2.5. 2.5 is smaller than 4.3, which is still smaller than 5. That makes sense with the kind of analysis of which line should be bigger. So, easy enough, right? Sine, cosine. Hopefully that's a review. Adding vectors. Some people get really bad around the axle about this. Honestly, you just add them up, x and y's. So there's their cool graphic, which I dislike. There's another version of it, which again I don't like because the arrow's all jacked up. So basically, you sit there and say, it's just like if you gave someone directions. Susie walks 3 meters north and then 10 meters east. What was her displacement at the end? Well, I don't have to go from here to here to here. I can just say she started here and went to there. However, we'd have to do a little bit of math. So there is how we write it out, because again, you start with an equation. Same idea, you can subtract them. Whoa, cool little graphics. Not really. And again, there you go. Addition and subtraction. So again, I'm not a fan of this problem, but we're gonna go through it because it's in a slideshow. I'll probably cut it out, but so river is going 3 meters to the west, and you're gonna try and cross the river. Now, if you put them both together, guess what? Are you gonna go end up going straight across the river? No. You're gonna try and go the resultant velocity because it's pushing you 3 meters that way. You're going 4 meters that way. For those people who couldn't trig, 3, 4, 5. So, resultant is you're traveling 5 meters per second that direction. Oh, and again, see how quick that was? I forgot the angle. So in this case, the tangent of your angle is 4 over 3. Tangent of theta is 1.33, or you can do the inverse tangent, and you get an angle of 53.1 degrees. We'll talk about that as well. Another version of the text actually has the inverse of delta y over delta x is another way to find this equation out. So projectile motion, the fun part. I love projectile motion. There's so many things you can do. A lot of my examples are throwing things off the roof, some cases students, but they haven't let me try it yet. I don't know, whatever. Let's change that. I'm sorry, I was blocking part of the screen because my big head's in the way. And it won't let me change the size of my screen. Okay, cool, you only get half my head. Yeah, it's okay, you don't need to see my huge forehead. So basically projectile motion, two-dimensional space, but it makes life a lot easier when we start breaking it down. So examples. The first one we'll study is objects thrown off a ledge, and typically we'll throw them straight off a ledge. A little bit easier scenario than projectiles launch, and you'll see why. Because if I throw an object that direction, straight off a ledge, following the blue, the constant velocity, is anything slowing it down if we ignore air resistance? Likewise, is any part of my velocity down? Again, the answer is no. It's a constant acceleration because of gravity. So example, the great classic question, if a bullet fired out of a gun is shot straight and a bullet is dropped at the exact same time, which will hit the ground? In theory, all things being perfect, no rifling of the bullet, no twist of the bullet, no elevation of the bullet, and the ground being flat all the way across, they should hit at the same time. I think I want to try it, but I can't. So, two separate motions, one is in the x, one is in the y. So, we will play with this equation a lot because honestly, what happens? Planet with no gravity it should keep going in the same velocity, correct? Same velocity, same direction, forever and ever and ever. Newton's laws, right? However, with gravity, it's going to start to come down. This is in y. So physics in general uses 9.81. AP Physics will use gravity as -10, so -9.81, just to make the calculations easier. On the exam, they will actually tell you which one to use. Most of the time, you'll revert to -10. Just it honestly makes the math easier. So if you use the equation at time 0, squeaked back in here, at time 0, your velocity is 0. After 1 second, it's 10 meters per second. After 2, it's 20 meters. After 3, it's 30. After 4, it's 40. 5, it's 50. All right. Notice that your height doesn't match because we have an equation for that. That being said, after every second, you gain another 10 meters per second. Okay? So, what's the path of the ball look like? Put them together. Do-do-do. Cool little graph. Do-do-do. I wish we could do that for every one of them. Anyway, so you have a graph that shows the real path of the ball is more of an arc. We should be able to follow it. We also should be able to calculate the velocity at any point in time. Again, you have a rise over run. You have a velocity of 50 meters per second. Get my little pointer out. Just using this example here. 50 meters per second, velocity in the x, this velocity in the y. You can find out what the resultant purple is. Likewise, you can find out resultant purple here as well. And what we'll typically do is find the resultant at impact. Now I know everyone's like, well, the velocity is 0 when it impacts the ground. Yes, but no. We want the fraction of a second before it hits the ground. Smarty pants. So, here we go. Tennis ball is thrown horizontally off a cliff. Assume the gravity is blah, blah, blah. Do you get all that? And we're going to go through another example. We're going to go through this one with everybody here. So, first we'll start with A. If the ball's velocity outright is 30 meters per second, is anything slowing down? Nothing's slowing it down. At 4 seconds, it's still 30 meters per second, yes? Cool. Hopefully that makes sense. The ball's vertical velocity at 4 seconds. So we start here on the left. Again, we write out everything we have. We know the velocity is going down. Velocity initially, v naught, in the y direction. I would have just put a y there. What is v final in the y direction? Do we know height? No. We know acceleration, we know time. So the best equation is this one. We know acceleration is -10. We don't know this. We know that's 0. We know our time is 4. -10, bring the 4 over, 40. Bring over 0, we're good to go. And again, using this setup for the equation helps out a lot. Okay. Now we're on C, the ball's speed at 4 seconds. Well, we just found this was -40. We know it's 30. A squared plus B squared equals C squared. Oh, they didn't write the equation, I forgot. Shame on them. So, finding the 50 meters, and hopefully that makes sense, because you go, that's a 3, that's a 4, 3, 4, 5, 50 meters per second. And then again, the angle. The inverse tangent, 4 over 3, 53 degrees. Next one. E. Horizontal displacement of the ball. Horizontal displacement from start to end. Did anything slow it down? Nope. So in this case, we have the velocity times the time. We know it was going 30 meters per second. It didn't speed up. It didn't slow it down. So there was 0 acceleration. in just the x path. So in this case, x is 120 meters. The vertical displacement of the ball. Well, we know it went from 0 to negative 40. We don't know delta y. We know acceleration is negative 9.81, or it was negative 10, and the time. So again, we can use almost the exact same equation, but in this case, we've changed the delta x into delta y. The velocity initially in the y direction is 0. The time is still 4 seconds. In this case, we do have an acceleration down 1/2 a delta t. 1/2 times 10 times 4 squared. 4 squared is 16. 16 times a half times 10 is 80. Notice negative y. Why? Because we started at the top and went down. And there's our lovely picture. All right, summary. Again, vector quantities, scalar quantities. Scalar quantities you will very rarely use. So, projectile motion. These are fun. And we'll talk more projectile motion. We will do so much more with projectiles. The one I showed you in here is very simplistic because you will never fire at a flat angle. I mean, no one does that. So, we will actually show one if I launch. And we'll talk about a lot of projectiles. So, this brings us to the end of chapter 3. It also brings us to the end of unit 1. That being said, there's a ton of things we need to make certain you know before the exam. If you haven't checked out AP Classroom, I've talked about it in class hopefully 2 or 3 times by now. AP Classroom on AP Central is very good. You all have accounts. You all know how to log into it. And if I haven't mentioned it, shame on me. Ask me to mention it because I have forgotten. Hopefully you have it. Hopefully you had it for a while. So it's another practice tool that will help you do really well in the AP exam. So I look forward to seeing you in class, and I'll tell you right now, we're in the middle of it. We've got things going. I think you're doing really well. So far, so good. Everything's good. If you have questions, as always, email me, put them on the links. Talk to you then.